Hello, my name is Cheng and I'm a PhD student at Purdue University. Today I would like to present our work, Recompose Image by Evaluating the Crop on More Than Just a Score. This work is done in collaboration with HP. Image recomposition is a task of cropping an image to a desired aspect ratio. This is considered an important step because the composition of the original image might not be satisfying enough, or a desired aspect ratio is required. There have been many existing methods that try to automate the cropping process, which learn to predict the best crop by being trained on large-scale datasets. Usually, these datasets provide only crops and their scores. However, there's still a problem that exists with these methods. Since the datasets provide crops and their scores only, it could become harder for the model to learn the aesthetics of an image. Similar features might be extracted by the model for two images of the same point of interest, but the ratings might be different due to a slight difference in the location of the point of interest. Also, these data-driven methods are not explainable in the inference stage. They are not capable of providing reasons why the predicted best crop is the most attractive one. Therefore, a method of enriching the ground truth should be proposed. To enrich the ground truth, we chose to extract more information from the image, and we believe the locations of points of interest and distracting elements are important, where saliency detection could be helpful. However, saliency detection methods do not distinguish between points of interest and the distracting elements. For example, you may notice that it is impossible to tell whether it is a point of interest or a distracting element from the saliency map. First of all, in our work, we assume that given a crop, the original image can be divided into 10 regions, where 9 regions are inside the crop and the 10th region is outside the crop. Then we propose a 10-layer score map, which has the capability of differentiating the points of interest from the distracting elements and can be generated from the existing public dataset. From the final ground truth 10-layer score map, it can be observed that the distracting hand receives high values in the 10th layer while receiving low values in the 9th layer and is not activated in the rest of layers. This indeed validates the purpose of the score map, which is to show the location where the salient object should be placed to maximize the score of the crop. In this example, the hand receives high values in the 10th layer, so it is considered distracting and it should be excluded from the crop to maximize the score. This slide shows the architecture of our proposed model. The inputs are simply the original uncropped image and the coordinates of the crop candidates. And outputs are the 10-layer score map of the original uncropped image and the score of the crop on a scale of 1 to 5. We use 3 metrics to compare our method with others. Top-end accuracy measures the proportion of the time when the true best crop is among the top and predicted best crops. Here report when n equals 5 and 10. Pearson correlation coefficient, or PCC, measures the correlation between the predicted and true scores of a list of crops. Spearman's rank correlation coefficient, or SRCC, measures the correlation between the ranks of the predicted and true scores of a list of crops. Among these methods, ours achieves the best performance. We also conducted another experiment by asking subjects whether or not they liked the best crop generated by different algorithms. To limit the experiment within 1 hour, we selected 100 images and compared 5 algorithms. Here are some examples of crops predicted by these algorithms. The value below each crop represents the percentage of subjects who liked the crop. With the help of the 10-layer aesthetic score map, our method is capable of placing the important saliency in the correct positions. To show that our cropping algorithm is explainable, we provide predictive 10-layer score maps for 2 images. For example, in the image at the top, the salient region of the palace is activated in the first 9 layers of the score map, but not in the 10th layer, showing that our model is capable of locating the point of interest. The salient region of the crowd is only activated in the 10th layer, showing that our model correctly predicts the crowd as a distraction. This indicates that our model can distinguish between attractive and distracting elements. In the image at the bottom, our method is also able to find the points of interest, which are the mountain peaks, from the panoramic image, and predict the reasonable best crop. In this work, we introduce a novel 10-layer score map, which can be generated from crops and their scores in existing public datasets. This 10-layer score map allows evaluating crop on more than just a score, and guides our model to learn the aesthetics of crops. The experiment we conducted showed that our method achieves the best performance.